Hi, this video is a continuation of the previous video where we've looked at in introduction to root locus, what is a root locus, and we've principally looked at the 5 rules which allow us to sketch root locus. So in this video, we're going to focus now on root locus refining, where we are able to we're able to calculate things like the breakaway point, the geometric crossing, and there'll be a topic which we cover, which will deal with angle of departure and arrival at complex poles and zeros. So we're going to look at that. Before we start on these topics of refining the root locus, so what I'm going to do first is do a small recap of what we did earlier by considering a few of examples we've done earlier, and let's see how these 5 rules we've looked at in the first part of the video actually apply. Yep. So this is one of the examples we've looked at where you had an open loop transfer function kgh was as follows, and from there, first thing you would do is you would find open loop poles. So they are 0, -2, -4, and then open loop zeros at -1, -3. Now, if you apply rule number 1, immediately we see number of branches that we have are 3 because you have 3 poles here. So on your root locus, you will need to have 3 branches. Now, straight away after finding your open loop poles and zeros, you would first put them on the complex plane. So we're going to represent the poles as crosses and the zeros as circles. So if you go back, so you have poles at 0, -2, -4. So 0, -2, -4. Okay, and then you have zeros at -1, -3. So zeros at -1, -3. That's the very first step you would do. You would put your open loop poles and zeros on the complex plane. Now, next step, rule number 2 is symmetry about the real axis. So we have to bear that in mind as we're sketching the root locus, that what we put on top of the real axis would also be reflected on the below the real axis. Now, let's try to apply rule number 3 now. This says that parts of a real axis forming part of a root locus would be found by applying the principle of odd number of poles and zeros. So these are the poles and zeros we put on the complex plane earlier. So rule number 3 tells us the left of an odd number of poles, finite, not complex. Later we're going to come across a situation where we get complex poles and zeros, and these don't come in rule number 3. We are just dealing with the finite poles and zeros on the real axis. Okay, so if we take this one, so this is the first pole, so this is odd number of poles or zeros. So this part here is going to form part of root locus. And then as you cross this 0 here, you're now into an even number of poles and zeros. So this part here, from this 0 to this pole here, doesn't form part. As you cross this pole again now this is the third pole or 0. So this part here is going to start, this part of the axis will form part of a root locus. And as you cross this 0 again, now this is a fourth pole or 0. So this part would not form part. And then as you cross this pole again, now this is a fifth pole or 0, which is found on the real axis. So this part of the real axis would form part of the root locus. So a very fundamental and very important step is to find which part of your real axis form part of the root locus. And in this case, we found these 3 segments here of the real axis would form part of the root locus. Okay. So next step here, if you just go one slide back, is rule number 4, which says that the root locus begins at poles and ends at zeros. In the previous step, we have 2 branches already ending at zeros. If we look at these ones here, so we know the root locus would start at poles and end at zeros. So already you have one of it here, just starting at this pole, ending at this 0. So you can put an arrow here. This one again, so this pole here is the branch for this particular pole is starting at this pole. This for gain is go to 0 and would end here for again k is go to infinity, so it's going to move here and go here. So already we have the second branch. So both of these 2 poles already have their respective zeros. Now this branch here, as we see, it is moving to the left, so would need to have a 0 at infinity, because we say all poles have to end at zeros. So this is what this line is saying here. From the previous step, we have 2 branches already ending at zeros. It's these 2 here. Now, one of the branch has no finite 0 to go to, and hence goes to infinity. Since there's a path going to infinity, we can apply rule 5 to find asymptote angle intercept. Let's try to do that. So we've seen rule number 5. We have these 2 equations here, which are quite straightforward to apply. So if you want to find the intercept of asymptote, so you have one asymptote, you do the sum of poles minus sum of zeros. So it's going to be 0, -2, -4, sum of poles minus sum of zeros. So you get here minus 6 plus 4, so you get minus 2, and then in the denominator it's the number of finite poles minus number of finite zeros, so 3 minus 2 get 1. So the intercept is going to get minus 2. In this case, we find the intercept is not that important here because we have just one asymptote. Now, the angle is important for us. So the angle is an odd multiple of pi over the same denominator we had for the intercept, so 3 minus 2. So as we replace different values of n here, starting at 0 and then 1, 2, 3. So if you replace n by 0 here, we get pi. If we replace it by 1, we get 2 times 1 plus 1, so 3 pi. So already here we're having sort of a periodicity here where we're adding 2 pi, so we can stop. You don't need to move it to 5 pi. So we're simply saying here the asymptote angle is pi. So if we go back here, what are we saying here? The asymptote that we have is going to go along the real axis because this angle is 180 degrees, is pi. So this is simply saying here this path here is just going to follow on the real axis itself, going to. This is what we can conclude. So this is the final root locus. Quite simple. This is the very first example we considered because this is going to be a root locus. If your root locus never goes into the complex plane with g omega values, with imaginary values, it always have real values for any value of k you choose to put in this transfer function, in the characteristic equation. The solution, the poles would always be real. And you can see from this diagram as well, your root locus never crosses into the right half plane, so this system is always stable. Now, second example we considered, again, as we were starting with root locus was this one. So let's again quickly apply the 5 rules just as a practice for you. So the first thing again would be to find open loop poles. In this case, your h is equal to 1 here, so it's not contributing any 0 pole. We have poles at 0 and minus 10, and we don't have any 0 in this open loop transfer function. So if you say rule number 1 is going to have, you have 2 branches. Yep, so because you have 2 poles, you will have 2 branches. So as we've said earlier, the first step would be to plot your open loop poles and zeros on the complex plane. So in this case, there are no zeros. So you have these 2 poles already put there as crosses. So on the real axis is 0 and minus 10. Okay. So rule number 2 is going to be symmetry. So again, we have to bear in mind what we draw above should be the same below. Now, rule number 3, very fundamental again, you will be seeing what part of a real axis form part of root locus. So this is pole number 1. So from here to here, it is still odd number of poles, no zeros. And then as it crosses this pole here is now pole number 2. So this part of a real axis will not form part of root locus. So what we're saying here is this segment of the real axis form part of root locus. And we know that root locus will start at poles and end at 0. So it means you can put an arrow here and arrow here. So these two are moving away. When k is 0, this is where the root locus would be. And then as you increase your gain, it's going to start moving out here. So as these two paths are joined, you expect it to break away at some point into complex plane because the poles would have to end at zeros. And in this case, we have 2 poles and we don't have any finite zeros, so they would need to go to zeros at infinity, as per rule 4. This is what you just said. So root locus begins at poles and ends at zeros. So there are 2 branches starting at the respective finite poles in the real axis, but no finite zeros to go to. Therefore, they need to go to zeros at infinity. Therefore, we have 2 paths going to infinity. So this is where, since you have paths going to infinity, you can apply rule number 5 now, which allows you to calculate the intercept and the angle of these asymptotes, which the respective paths will follow to go to infinity. So if we just apply the first equation to get the intercept, so 0 minus 10, sum of poles, there's no 0, and then over the number of finite poles minus number of finite zeros, so it's 2 minus 0 because we don't have any finite zeros, so minus 10 over 2 equal to minus 5. So what are we saying here? The asymptote would cross here. You have 2 asymptotes because you have 2 branches going to infinity. The asymptote is going to cross at minus 5. What this is saying. Now let's find the angle now of this asymptotes. So it is 2n plus 1 pi over 2 minus 0. So if you replace your n here by a 0, you get pi by 2. If you replace your n by 1, you get 3 pi by 2. If you replace your n by 2 now, you get 5 pi by 2. We see now pi by 2, 5 pi by 2 is already 2 pi cyclic, so we can stop. So these are the 2 angles of asymptotes. It's saying it's pi by 2 and 3 pi by 2. So it means it's at minus 5, and one asymptote has an angle of pi by 2. And the second asymptote now would have an angle of 3 pi by 2, which is 270 degrees. this is what I just explained, and these are the two arrows I mentioned earlier because the root locus would always start from the poles and move away from it. So based on this now, you can sketch the root locus easily, and this would be a breakaway point. Now at this point, we don't know how to calculate this breakaway point. Maybe your root locus is going to break at some other point, but in this case, it's going to break at this point here, clearly. But later we're going to see how do we calculate this breakaway point using specific calculations. Okay. Now at this point, we're saying your root locus is having asymptotes here of 90 degrees and 270 degrees. So this is why we got a root locus like this. Remember when we were discussing that earlier, this is what we drew. Now maybe it makes a bit more sense. How come we are able to sketch this root locus? When we started this chapter, remember we actually explicitly calculated this root locus for gain k is equal to 0, 5, 10, and so on, and then we were able to draw it. But now, based on the 5 rules we've discussed, you are able to sketch this root locus without explicitly finding the poles. That's very interesting. So we've revisited the 2 examples we've considered earlier as we were introducing this chapter, and we applied the 5 rules, so I hope it's a bit clearer now. Now, the third example we considered, so this one where we got a root locus, which was like a circle. So we'll come back to this example as we go along now. We'll use example to as a work example, as a case study for illustrating the refinement of a root locus to calculate certain specific features, like I've said. Let's go straight away into that. Now, after you have sketched your root locus, or as you're sketching it, maybe there are certain parameters you want to calculate to be able to better sketch it. So this is what we're going to try to find in this section of this chapter on root locus, which will allow us to be able to calculate certain features with more accuracy. So we're going to see what these features are. Basically, they are the breakaway and breaking points. So what are breakaway and breaking points? If I just go back here, so when you have 2 poles like this and they are joined together, so they will have to break away at some point. Now if you have now 2 zeros and the root locus has to go to these 2, they're going to break in. If I just take this example we had earlier, maybe back here, in 1 minute. Just to illustrate, there's one very good example to illustrate what are the break-in and breakaway points. Yeah, so this one. Yep, so this is a very good example to illustrate what is a breakaway and breakaway point. So here we have two poles. So we have the 2 branches moving out. So at some point you have to break away here, like we said earlier. And this now are 2 zeros, and we know that the root locus has to end at these 2 zeros. So this is a breakaway point, and then the paths have to come back, and so this is the break-in point. So one of the calculation we'll be doing as part of refining the root locus is try to find actually at what point this is breaking away and breaking in, because we can't assume that it is actually midway between these 2 or midway between these 2. That's not correct. So we need to calculate this specifically. This is one of the refinement we'll be doing as part of the calculations we'll be discussing. Okay. And also another refinement we're doing is a geometric crossing. So if your root locus is breaking into the right half plane, so at what point it does that. And another important topic for us are angles of departure from complex poles and arrival at the complex zeros. So we're going to discuss that more in detail as we come to this topic. Now, before we can move on, I would like just to present a few fundamentals for us to be able to refine the root locus. So one of them is dealing with complex numbers. So let's say we have a function f as follows, and we would need to work out the value of this function at a given point, let's say minus 3 plus g4. So one way to do that is just to replace minus 3 plus g4 in this expression here, like I've done here in quite details. You just replace it here, and you just simplify, and at some point you have to multiply by the complex conjugate of a denominator, and then keep on simplifying, and you reach to a result like this. Now, when we have the value complex as shown, of course, if you have a magnitude and an argument, so you can work it out. But instead of doing it in this way, by computing, by using mathematical method, which involves quite a lot of manipulation, you can do that graphically as well, which is of more interest to us because we're dealing with a root locus, and root locus is a graphical method. Let's see how we could have solved this problem here of finding the value of a function at a given point using a graphical method. So let's try to do the same thing now using graphical method. So when you get a function in this way, we know we can find the poles. So the poles here are 0 and -2. And you have a 0 here, which we have shown the circle as usual. We put it -1 because this is a 0 at -1, so we put a circle here. Now let's say we want to find the value of this function at the point -3 plus g4. So we have put that point of interest here, -j plus -3 plus g4. So what we do next, we link the poles and zeros of your expression you're trying to evaluate to this point of interest. If you join these here, it means you've got three vectors. Now these vectors have to start from the poles to the point of interest and not the opposite. So it can't start from the point of interest and go to this pole here. It's always from the poles and zeros to the point of interest. Now if you have these three vectors here, you can work out each individual angle, first thing, and you can work out the length of these vectors. So let's do that. So if we want to find the vector originating at the 0 at -1, so the length of it is going to be, you just have to take, so this is 2 here and this is 4, so 4 squared plus 2 squared, so you get 16 plus 4 is the square root of 20, and then how you get 116.6 degrees is simply finding the angle it's making here. So first maybe most likely you find this one, so it's tan inverse of 4 over 2. And then take 180 minus the tan inverse. This is why you get at 116.6 degrees. So similarly, you can work out the length of this vector here. So this one is going to be 3 squared plus 4 squared. So square root of 25, you get 5. And if you want to work out this angle here, it's always from the real axis and then to the vector. So it's going to 180 degrees minus tan inverse of 4 over 3. This is where you get 126.9 degrees. And similarly for this vector here, you can work out its length. So it's 1 squared plus 4 squared square root, so square root of 17. And where you get the angle 104.0 degrees is simply 180 degrees minus tan inverse of 4 over 1. So you see where you get 104.0 degrees. Now let's see, once you're able to find the length and angle of these vectors, how can we evaluate now the values this function takes at this particular point? Now it's become very straightforward. You just have to take the length of vectors from zeros in the numerator, because this is square root of 20, it was corresponding to a 0. We know 0 always open the numerator. The square root of 20 is in the numerator. Now in the denominator, you put the length of vectors for poles, so it was 5 and square root of 17. And if you evaluate this, you get the 0.217, which we got earlier. Okay. Now similarly, if you want to find the angle which this point is, the argument of this point that is creating in the function we're evaluating, you now simply take the sum of angles, but bearing in mind for 0, since in the numerator you contribute a positive angle, so 116.6 degrees is positive, and these two angles will be negative because they're poles and the denominator. If you now take the sum of these angles, bearing in mind the cosine, you get actually the angle that you would get earlier, 114.3 degrees. 4.3 degrees. So a very convenient method for you to evaluate the value of a function at a given point is to construct vectors from the zeros and poles of that function, and then finding the length of these vectors and angles of these vectors, and then evaluate it accordingly, bearing in mind zeros on in the numerator and poles on the denominator. So when you work out the magnitude here, you would put the length of zeros in the numerator and the length of vectors corresponding to poles and denominator. Whereas for angles, all angles for zeros will be positive and angles for poles will be negative, and then you would get this value. We're going to use that later as we evaluate the gain of the system. This is one method we'll be using to find the gain, but also the angle consideration we had applied here will be very useful later when we find angle of departure and arrival, like we said earlier, which is one feature we find when we try to refine the root locus. So let's now apply this method. We just discussed about finding the value of function using graphical method. So this is one example we considered earlier. As we were introducing the chapter, and we've sketched a root locus. Remember, we did a table like this earlier where we did not apply the rules, but we actually saw the poles explicitly, and we found the reverse poles and we sketched it. So this is something we did earlier. And also remember very well, when we started chapter, this was the fundamental equation for us. A closed-loop transfer function is of this form. This is a characteristic equation. This is actually the root locus that you're plotting as k is varied. Now from here, if 1 plus kgh is equal to 0, so kgh is equal to -1. So this is where we got that fundamental relationship where the magnitude of your kgh should be equal to 1 and the angle should be an odd multiple of 180 degrees, because -1 is the left of the origin, so its angle is always a plus or minus 180 degrees or an odd multiple of 180 degrees. So this is the two fundamental relationship. Now the one of immediate interest to us is this one here. So this is simply saying here, if you want to find the gain at a specific point on the root locus, you just have to apply this equation where you send the GH on that side. Now, what is GH, which is actually a function we're trying to evaluate? And we've just seen we can evaluate this using a graphical method. So let's see how this works. Yep. So it means you can find the gain at any point on the root locus using that equation. So if you're able to find GH, which is a function of interest to us, and then just have to invert it, because 1 over that value you get your gain. So let's try to apply it for 1 point. So if we just go back here to that table here, we are trying to find what value of gain would we get. -5, but let's try to actually calculate it. So if we take a specific point, -9.47 and -0.53 on the root locus. Okay, so these are the two, if you look at this transfer function here, GH is as follows. So S into S plus 10. So this is what we are considering here, this one. So S into S plus 10. So first thing we do is you put the two poles that you have at 0 and -10. Now the point of interest we have is at S is equal to -9.47. So we want to know if at this point on the root locus -9.47, what value of gain do we get? If you just put that point here -9.47, so what we just said earlier, you're going to link this point that you have to your poles and zeros. So you link it to this one, and then you link it to this poles. I'm just doing it by my mouse here. I'm not actually drawing it, but I'm just explaining it. So -9.47 will be somewhere here. This is your point of interest where you want to find a gain. So -9.47 is here. You will link it to this pole here at -10, and you will link it to this pole here at 0. Okay. Now, what did we say now? If you want to evaluate what's a function GH at this point, in this case, you don't have any zeros. It's a 1 in the numerator, and then in the denominator, it's going to be the length of his vectors. So what's the length of vector from -9.47 to -10? So it's going to be 10 minus 9.47. That's a small length here. And what's the length of vector from 9.47, 10 to 0, sorry, at origin? Just 9.47 itself, 9.47 to 0. So you would take now the product of these two. So this is the value of that function GH at this point -9.47. And like we said earlier, if you want to find the gain, is 1 over this value. So 1 over this one, you just invert it, then you get the 5. So we know actually at 5, you have a gain of 5, we will get this point, but we have work opposite way to try to find the gain now given the point. So very powerful method now. If you want to find the gain at a specific point on the root locus, you can very easily draw. So let's say I wanted to find the gain at any point in root locus here. So I just need to join this point of interest to my poles here in this case, because we don't have any zeros, and you work out the length of these vectors and just apply this fundamental equation where it's always a length of zeros over length of vectors corresponding to poles, and then you invert it, you get the. Now, another requirement we've said is this one here. So every point you have on the root locus needs to have a contribution of angle equal to an odd multiple of 180 degrees. Yep. So if you were to apply the same principle we've done, let's say you take this point again, you would get actually 180 degrees. Okay. Does this mean that the sum of angles of the zeros minus the sum of angles of the poles must be an odd multiple of 180 degrees? So let's check with the point -5 plus 2.24. So if I just go back to this table again, this one, so we're saying -5 plus j2.24, which we know is in the root locus, but let's say we now want to validate if that point is in the root locus. How will you do that? So -5 plus j2.24 will be somewhere here. So -5 plus j2.24 is somewhere here. Okay. So what would you do now? You simply construct vectors linking your pole to that point and this pole to this point, and then you'll find the two angles that you're going to get. When you take a sum of these two angles, this should come to minus 180 degrees. So in this example here, we don't have any zeros, so there won't be any positive contribution of angle. We have two angles. Let me just try to show it again. So you have a point here, minus j minus 5 plus 2.24. So if you link it to this point here, and again you link it to this point here, the sum of these two angles that you get should be equal to 180 degrees. In a way, this is a fundamental mathematical expression. If you take the sum of an internal angle with corresponding external angle should be 180 degrees. Yep. So this is what you get. So this is something which you can easily work out. So just again to summarize what steps you need to take. So you draw poles and zeros of GH on the complex plane, and from the vectors, and then form vectors by joining the zeros and poles to the point of interest. So in this case, minus 5 plus j.24. And in this case, we don't have any zeros, so you have only two poles. And you determine the angles of poles and zeros and find the sum of these angles. Sum of zeros minus sum of poles. So it should be poles here. Sorry, this should be poles here. So if you get an angle which is equal to 180 degrees or minus 180 degrees, it means that point was on the root locus. Now, once you validate that this point is on the root locus, you can very easily find the corresponding gain for this point. So again, how you do that? So you have constructed here two vectors to be able to find angles. So if you find the length of these two vectors, and then you just find the length of them, and then you just apply something very similar to that. So 1 over the length of these two vectors, you should get the gain. So work it out and cross-check that you get a value of 30. Because we know it is 30, case 30 at this point, then we're now calculating and confirming the result. So one safe practice for you is check if the point minus 2 plus j2 is found in the root locus. If you look at the root locus here, minus 2 plus j2 would not be on the root locus if you look at it on the complex plane, but I wanted to validate it. So how come you would be able to validate that? Is simply you're going to put the point of interest here now, and then you're going to link this point to the two poles that you have, calculate the two angles you obtain, and then take the sum of them. So in this case, again, you don't have any zeros, so no positive angles. You have both angles will be negative. Now the sum of these two angles would not be equal to 180 degrees, plus or minus 180 degrees. So if it's not the case, it means that point is not on the root locus. So this is left as safe practice for you. So the next topic we look at now as we are refining a root locus is called real axis breakaway and breaking points. Now I explained that earlier. So if you have a point where two parts from a root locus from poles are joining together, so it needs to break away at some point because these two are joining together, it has to break away. And if again you have a point, a segment of your root locus, which is a real axis here, for it to be able to go to these two zeros, it will not typically go straight onto this two because you should satisfy the symmetry principle. So one of these paths cannot just go here, and then the second one goes here directly, because then it won't be symmetrical. So in this case, for us to satisfy rule 2, which is about symmetry, it means it has to be, you need to have a break-in point, and then from there it's going to move to the two zeros. So what we're trying to find in this part of the section of this chapter is how do we find this breakaway and breaking point. Again, I'm repeating that it's not midway between these two points, and this one again is not midway between these two points. You need to specifically find it. Maybe the case is midway, but it's not necessarily the case. So let's discuss the fundamental principles that we'll be using to find this breakaway and breaking points. Okay. Now, it's a small interesting comment here is the breakaway and breaking point would have an angle here. The angle is making when it's arriving will be always 180 degrees over n. So if n is 2, in this case it's 2 because you have two poles, there's going to be 180 over n over 2, so it's 90 degrees. Same comment for the arrival to 0, so the angle at which these two branches would arrive at the break would actually break away from this point to be 90 degrees. And for this case here, the angle actually is going to arrive here to the breaking point to be 90 degrees. So this we know. Yep. Now let's see what fundamental principle can we apply to be able to find this break-in and breakaway point. Now let's consider the first case where we're dealing with the breakaway point. Now let's look at this case here. If I just go one step back, we know we have a pole at -1 and -2. So this is what's shown here. Now we know at the poles, the gain are 0. This is what we know, is because the root locus start at the pole. So k is going to 0 here and k is going to 0 here. And as we start increasing the gain, now the root locus will start move to the away from the pole. So in this case, we say they start moving towards the breakaway point. It means at the breakaway point, you have a maximum of gain as far as the root locus is for real values of poles. Let me repeat that again. At the poles here, we know the gain is 0, so k is equal to 0 and k is equal to 0 here, and then we start increasing the gain as for the root locus to move away from it towards the breakaway point. So at the breakaway point, this means you have a maximum value of your gain for the range of values of poles on the real axis. Of course, after this point here, your gain will keep increasing. When your root locus has broken into your imaginary part of the complex plane, fine, your gain k is going to keep increasing. That's fine, because your root locus start at k is equal to 0, and then it has to keep increasing until it goes to infinity at the zeros. But what we're saying here, for that segment where your poles are real on this part here, you have a maximum gain at the breakaway point. Now, a similar analysis, let's do similar analysis for the breaking point now. We know now at the zeros, the gain k will be infinity, because this is where the root locus ends. So this is a converse now of the breakaway point. It means when your root locus actually arrives at the breaking point, the gain has to keep increasing to be able to reach infinity at these two zeros. So again, for the segment here of poles that are on the real axis, so you have a minimum point at the breaking point, and then as your gain keep increasing. It means if you wanted to find the break-in and breakaway point for range of values of your poles which are real, because we are dealing only with this part, we're not dealing with values which are actually in the imaginary part of a complex plane. So for this segment here, okay, at the breakaway point, you have a maximum point. For this segment here, at the break-in point, you will have a minimum point. So it's two stationary points that you would have at the break-in and breakaway points. Okay, so this is what we've just discussed. The main finding was you have maximum point here at the breakaway point and a minimum point here at the break-in point. Okay, so let's apply this principle now on an example to find actually the break-in and breakaway point. So this is your open loop transfer function. We can expand and bring it to this form. So this is what's shown here. So based on the 5 rules we've discussed already, you are able to actually draw this root locus. Now, if you apply rule number 1, 2, 3, 4, 5, so there's no rule number 5 to apply here because you have 2 poles, 2 finite poles, 2 finite zeros, so they will be ending here. There are no paths going to infinity. And there's symmetry, and then you can determine what this segment is. But what you can't at this point find out is where that breakaway and breaking point is specifically. And if you knew it, you'd be able to sketch it better. And there's another point interesting here. If we could find the J-omega crossing here, it would be interesting for us to sketch it better. This is what we're going to look at next. But for the time being, let's see how we can work out this breakaway and breaking point. Now, one fundamental equation we've seen earlier for the characteristic equation is 1 plus kgh is equal to 0. So if you send that minus 1 on the other side, you get kgh should be minus 1. Okay, so kgh is what for this particular example we're considering. That's the equation here. So you can see k, this equation is going to minus 1. Now we're replacing s here by sigma for the simple reason that we're saying that we are dealing only with real values of sigma. This curves here again are relevant, so you get a maximum here and a minimum here only for real values of sigma. We know s equal to sigma plus j omega. So by doing this here, we are enforcing that the result we want for sigma, for s, is only real values, because this minimum and maximum points we've got are relevant only for the real part of the real segment of our root locus, not when it goes into the imaginary plane. So if now you replace your s by sigma, and then you try to solve this one now. So how we do that next step? So you can find k in terms of just send on this side, just make k subject of formula. Now we want to differentiate because we have a maximum point and a minimum point to find with our stationary points. So you can differentiate this expression k here. So you have to find dk by d sigma. So here you're going to apply quotient rule. So this is your u and your v. So it's v squared over v du minus u dv. So this is a result we got. So make sure you work out the details here. So again, this is u over v. So applying quotient rule for differentiation. So it is v squared in the denominator. The numerator will be v du minus u dv. So if you do that, you will get a final result like this, which would equate to 0. And then if you solve that now, this denominator would of course go to 0. Then you get a quadratic. And when you solve for sigma, you get minus 1.45 and 3.82. So we are saying here this is minus 1.45, and we're saying this is 3.8. So in this, using this method here, you can work out your breakaway and breaking points. Now, another method maybe you would use more, because this one would avoid the differentiation step. This comes from the field of mathematics, where we are able to find the breakaway and breaking points simply by solving an expression like this. So what this one is simply saying here, if you take a sum of all your 1 over sigma plus all your zeros, so zi here will be the negative of the 0. So in this case here, if your 0, for example, is at 3, so this is going to be minus 3 here. And if you have a pole at 5, so the negative of a 0 will be minus 5. So it's going to be minus 5 here. And same comment now for your poles. So this pi here is a negative of the poles. It's very easy to apply actually. So let's do that for this example again. You can clearly see here, these are actually the values we talk about. So if you have a 0 at 3, you have minus 3. If you have a 0 at 5, you have minus 5. So basically, this is going to be 1 over s minus 3 plus 1 over s minus 5 is equal to, so this sum for the poles are on the right hand side, is equal to 1 over sigma plus 1 plus 1 over sigma plus 2. This is what this expression, this relationship is simply saying. So we actually are avoiding this differentiation step. If you apply it on the example we just looked at, so this is again the expression, the relationship you're using now to find the breakaway and breaking points. So this now is your open loop transfer function. So what this part is saying is 1 over sigma, so sum of 1 over sigma of all the negative values of your zeros. So it's 1 over sigma minus 3 plus 1 over sigma minus 5 is equal to now right hand side of same thing now for your poles. So your poles are at minus 1, so minus of minus 1, so it's 1 over sigma plus 1 plus 1 over sigma plus 2. Now you can just make common denominator, simplify. You will get this equation here to solve, which is exactly the same as you have here. Yep, so you expect to get the same answer. So you could use differentiation to solve your breakaway and breaking points, or you could use this fundamental relationship, which again comes from the mathematics, to solve breakaway and breaking points. Okay, so that's the part on real axis breakaway and breaking points. So you will have chance to apply that on further examples later when I send it to the sheets. Now, next point we want to find as part of refine this root locus is a geometric crossing. Like we said earlier, it's a very important point for us because this marks the transition between the stability and instability. Now, based on the tools we've discussed already, what method can we use according to you to solve that geometric crossing? So this is what I put in green here to get you thinking. Now, you would recall when you were doing the Rath-Hurwitz criterion, if you get a row of zeros somewhere in your Rath table, this is an indication that you would have actually a geometric crossing. It's not necessary, it is a geometric crossing, but if you do have a geometric crossing, you would need to have a row of zeros in your Rath table. So we can use this very simple principle here to actually find the geometric crossing. There are other methods you can you find in textbooks where you can solve the geometric crossing, but we are considering here the Rath-Hurwitz method to do that. So let's take an example here. If you have a unity feedback system with this following open loop transfer function, so you can very easily apply the rules here. So first step, you're going to have poles at 0, minus 1, minus 2, minus 4. So 0, minus 1, minus 2, minus 4. And then you would have here a 0 at minus 3. So what you've done here, you can apply your various rules to find out the segment here. This is not part of the root locus. Then you have this one is to the left of odd numbers, so it's a third pole here, so this forms part of root locus. Now when you cross this 0, now you are the fourth pole or 0, so this part doesn't form part, and as you cross this one now, it's a fifth one, so it forms part until infinity. So you can very easily see now you have 4 poles and 1 0, so you have 4 finite poles and 1 finite 0. So immediately you can see this pole already has a branch ending in it is 0. Now the remaining 3 branches will need to go to infinity, so you can apply the rule 5 to find the angle intercept of these ones. So you would find that this is -4/3, and the angle of your asymptotes would be pi. So this is the 1 here, and you're going to find 1 to be 60 degrees, so pi by 3, and you're going to find 1 to be 360 degrees. Okay, now once you do that, then clearly this path is going to infinity. Then this one here, you have a pole and a pole. This part of the axis is part of root locus. So you would need to have necessarily a breakover point here. So you can use technique we've seen earlier to find this breakover point. But the point of interest for us is here, if it is breaking away here and it needs to go to that, to these two asymptotes, it would definitely need to cross the G omega axis. So what you're trying to find out in this case is where it's actually crossing these G omega axis. Yep. So from your unity feedback system, from the open loop transfer function, you can find your closed loop transfer function, because of course your graph table is constructed from your closed loop transfer function from the characteristic equation. So if you do that, this is the result we're getting. Now from this polynomial in the denominator here, in terms of k, of course, because we're not fixing the value of k, we want to find the value of k for which you have a G omega constant. Remember, the root locus is the path of your poles as you vary k. So from a characteristic equation, let's construct a graph table and enforce the condition to get a row of zeros by choosing a suitable value of k. So if you do that here, if I just go back here, so you have for the S4 row, you have 1, 14, and 3k. So 1, 14, and 3k. For the S cube row now, you have 7 and 8 plus k, so 8 plus k. Wherever you have blanks here are simply zeros. If you work it out now using the method we've done, so if you take 7 times 4 minus 1 times 8 plus k divided by 7, so you can clear out the denominator and so on, so you're going to get these results. So make sure you cross-check that you're getting these values, because we've covered this topic in your chapters. Similarly, we get 21k here. Yep, you will simply take 7 times 3k minus 1 times 0, but again, you're normalizing here, you're multiplying by a common factor 7 to remove a 7, and then this is very important for us. When you've got s squared row here, you can work out s row, and similarly the s row. Now, for us to have a row of complete zeros, we're going to choose this one here, because for us to have a G omega crossing, it means we need to solve a quadratic equation. Yeah. So if we choose to make this row become 0, because you have a 0 here for this blank, so when would this expression be 0 and when the numerator is 0? You can set minus k squared minus 65k plus 720 equals to 0. You find the value of k, you will get a positive and a negative value, but we know gains are starting from k is equal to 0 to infinity, so we don't take the negative value. We take k is equal to 9.65. Basically, what we're saying here, if you choose k is equal to 9.65, you plug in here, you're going to get a 0 here. So what do we do normally when you are solving, when you are trying to use graph table and use row of zeros? Yep, we're going to go one step higher in the next row here, and then we're going to form an auxiliary polynomial. So that's exactly what we do now. From this value of k that you're getting here, you form an auxiliary polynomial of this row here. So this is what we do next. So if you see this row here, so it's 90 minus k s squared, and this coefficient here would not be s, because this is s squared. We have only even powers of s. So this is going to be s power 0. After s squared, you get s power 0, so it's a constant here. So 90 minus k s squared plus 21k. You replace the value of 9.65 here and here. So this is what you get, and when you solve s here, you will get imaginary values, imaginary roots. So what we're saying here are the crossover points will be plus or minus j 1.59. So this is plus or minus j 1.59. Yeah, we use the occurring complex conjugate. That's the root locus crosses the G omega axis at a gain of 9.65. So when you are at 9.65, this is where the root locus will cross the G omega axis. Now let's look again at how the root locus is actually progressing as we start the gain of k is equal to 0 and we start increasing it. So we know at all these poles here, these 4 poles, the value of k is equal to 0. As you start increasing your gain k, then there's one path going to this 0 at minus 3 here when your gain is infinity here. Then you have one path going to infinity here on the left here. So that's not a problem. All these 2 paths are actually staying on the left half plane. Now this one is of interest to us because this is where gain k is equal to 0. You have a breakaway point somewhere which you can find using the method we discussed earlier. But then after this breakaway point here, you will have the 2 paths now actually transiting into the right half plane at a specific value here. We say this is J 1.59 and this is minus J 1.59, but interestingly, the gain K is equal to 9.65. So if you want to comment on stability, it means the root locus is showing to us the system is stable for values of gain K starting with 0 until 9.65. If you exceed 9.65, the root locus will go on the right half plane and then it goes instability. Because we know if you have poles on the right half plane, even one pole is enough to create instability. So if you want to comment on stability of systems, again, K should be between 0 and 9.65. Now, the last topic that we're going to look at in this section on refine the root locus is angle of departure from complex poles and arrival to complex poles. Okay, let's consider this root locus which we've just looked at. Okay, now what do we mean by the angle of departure from complex poles and angle of arrival to complex zeros? Is simply this one here. For example, if you take this pole here, you can see the root locus is moving in this direction here, so this angle of departure is simply 0. And for this pole here, the root locus is moving to the left here, so the angle of departure is 90 degrees. It's very well shown on this diagram here. So the angle of departure from this pole here is 0 degrees. For this one is 90 degrees. Now the angle of arrival now to zeros, because when two poles arrive, the root locus arrives at poles, arrives at zeros and departs from poles. So if you look at the angle of arrival, this particular pole for this particular 0 here at S is equal to 3. So we can see it's moving here into it. So from the right to left, so the angle of arrival to this 0 would be 90 degrees. And the angle of arrival to this particular 0 here is going to be from the left to the right, so it's going to be 0 degrees. So we can see here when you have poles or zeros on the complex plane, on the real axis, it's not difficult to find angle of departure for poles and angle of arrival for zeros. Now, so now it should become clear why we are talking about complex poles and complex zeros. So if ever any poles or zero were actually having imaginary values, then it will not be necessarily 90 degrees. It's going to be more complicated to find it. So we're going to use methods now. How can we work the angle of arrival to complex zeros and angle of departure to complex poles? Okay. This is why, so again, when you have all the poles and zeros on the real axis, it's straightforward to find it. So when the poles and zeros are on the real axis, the angles of departure or arrival respectively are easy to find out. Still, if you wanted to find out the angle for one of the pole, how would we do it? So using the methods we've discussed earlier, where you have a point of interest to a function, to a transfer function, and you want to work out the angle that a particular point is making on this function. Remember we said earlier you can construct vectors and then you can take sum of angles from zeros and poles and then find out angles. So we can apply the same principle here. So in case you wanted to find the angle of departure, for example, to this particular pole here we're considering. So we've looked at all this earlier. I take a sum. So let's say we want to work out the angle of departure from this particular pole here that you have at -2 on the real axis. Yeah. So what do you do now? So this becomes your point of interest because you want to find the angle of departure at this particular point. So I've drawn here 3 root locus simply to show you the vectors that we need to draw because it will all overlap if I put everything on one root locus. So the first vector you will construct will be from this pole here to this one. Okay, so each angle would be 90 degrees. So the angle of this vector we've drawn from this pole to the point of interest is 90 degrees. The next one we're going to draw is from this 0 here to, again, the same point because it's at -2. We want to find the angle of departure. So this angle here will be again 90 degrees. Now, next we're going to draw a vector from the 0 at S is equal to 5 to, again, the same point of interest, and again the angle is 90 degrees. Now, when taking the sum of all these angles, so the angle for the angle we want to find here, let's be theta, angle at this point of interest. So we put a minus theta here simply because it's a pole. Yeah, because we know poles bring a negative angle contribution. So minus theta, and then this angle here will be minus because it's a pole. Now these two here are zeros, so the angles will be positive. And for this point to be on the root locus, because it is a root locus, it will be a pole, it has to be plus or minus 90 degrees. It's the odd multiple of 90 degrees. Now from here, you can solve for theta. You just stand theta on this side. These two 180 degrees are cancelling out. So it's 180 degrees plus or minus 180 degrees. You get 0 degrees or 360 degrees. Same thing. So it means angle of departure from this pole is simply 0 degrees. And this is what we said earlier here. We know it is 0 degrees. So this is a very trivial example if you want, but very clearly uh, describe how we can apply the same concept now if you were to find angle of departure from complex poles to angle of arrival to complex zeros. Let's take an example now to illustrate how we do that. Okay. So this is a work example here. So sketch a root locus for the following unity feedback system and calculate the angle of departure from the complex poles. So first step you're going to do, like we've said earlier, you have to find your the zeros and poles of your open loop transfer function. So you have a 0 at s equal to -2, you have poles at -3, and you have complex poles which you need to solve s squared plus 2s plus 2 equals to 0. So you're going to get -1 plus or minus d1. So first step you're going to do is put all these poles and zeros on the complex plane. So like we said earlier, you have a pole at -3, you have a 0 here at -2. So these are on the real axis, and then you have these two now, these two complex poles, the complex conjugate at -1 plus or minus g1. Now, when you apply rule number 3 now, to find out which part of the real axis form part of a root locus, so you have to deal only with the poles and zeros on the real axis. So these two here, these two complex poles, does not come into counting the number of poles or zeros to find the odd and even. So you start, and so this is the first real pole, the first real zero, and then to the left of it, it forms part of root locus, and then to the left now of this second pole, which is pole of 0. So this does not form part here, so immediately you have one part of a root locus is just starting straight from this pole and going to that 0, but that's done. Now you have these two paths here, which are from your two complex poles, they have to go to 0 at infinity. Yeah, because you have these two branches without any finite zeros in transfer function. So now the aim is to find angle of departure because we know they are going to infinity. You can use here rule number 5 if you want to find the asymptotes, intercept, and angle. We know that, but we want to know at what angle actually the root locus leaves these two complex poles. This is what we're trying to find out. If we knew that, for example, it could be making like this, or it could be moving in this way, or moving down and then moving up. So find out at what angle is departing from this complex poles. This is what we're trying to do. So let's try to find the angle of departure from this complex pole here. So what do? This becomes a point of interest. And next step, we have to join this point here, which is a point of interest, to the other, all the other poles and zeros. So we join this one here towards it. The same comment for this one. So this 0 to this point, and this complex pole as well has to be joined. So next we have to find all the angles. Now θ1 is unknown. This is what we're trying to find out. This is the angle of departure we want to find out. Angle θ2 here is actually 90 degrees. Yep. Now these two angles can be easily worked out. Yep, so θ3 here is going to be tan inverse of 1 over 1, and θ4 here is going to be tan inverse of 1 over 2. If we do that here, bearing in mind that poles would have a negative angle contribution and zeros would have a positive angle contribution, so minus θ1 here because θ1 corresponds to a pole, minus θ2 here because again θ2 corresponds to a pole, plus θ3 because θ3 corresponds to 0, then minus θ4 here because this is a pole. Okay, so my θ1 is unknown. This is what you want to find. This is the angle of departure we're trying to find to this complex pole. But we've said this θ2 is simply 90 degrees because these are complex conjugate. It's exactly below it. So you always start from the real axis and then you turn anti-clockwise to get the angle. We've said how to work out these two angles. So this one is tan inverse of 1 over 1, and this θ4 is tan inverse of 1 over 2. Now, if you find the sum of these angles, and for this point to be on the root locus, it would be on the root locus because a pole. It has to be plus or minus 180 degrees. So we're choosing 180 degrees here. You could have chosen minus 180 degrees as well. So we're getting an angle theta of minus 251.6 degrees. So we're saying here this angle of departure is minus. So you're going to turn clockwise now because it is minus. So it is minus 251.6 degrees. Or if you want it to be positive, you can add 360 degrees since it's 108.4 degrees. Okay, so in this way, you can very nicely find your angle of departure from complex poles or angle of arrival if you had complex zeros, you can similarly find angle of arrival to complex zeros. So if you have examples like this, now you can very easily applying the rule number 2 now by symmetry. If this is moving this way, you can very easily find the angle of departure from this complex pole as well. So this concludes this section here on root-locus refining and the whole chapter on root-locus sketching and refining. So I'll be sending out a tutorial sheet for you to practice for the examples. I hope it's been a very instructive session for you, and the reference for the slides I've been using, the examples I've been discussing are again from Norman Nees, Control Systems Engineering 6th edition. Thank you very much for your attention, and I'll be sending further materials to you, tutorial sheets and lab sheets later. Thank you.